Hello everybody and welcome to the Covalent Cymru revision sessions. The session this evening will focus on chemistry, GCSE Year 11, and the topic is bonding. My name is Rhian Booth. Today's session will be recorded and the recording and any relevant resources will be uploaded to the e-sgol website under Covalent Cymru tab. So thank you very much and we'll start the session. So topic is bonding, and let's have a look at the content of today's lesson. So types of bonding, bonding diagrams, properties, and questions and examples to finish off the session today. So before we can move on to this unit, we want to look at some important things that you need to know before we can even attempt some bonding questions. And I've got some things here on this slide. So A, to begin with, is the periodic table of elements. Now, I'm not saying you need to remember this off by heart, of course. This will be in your exam paper. However, you do need to know how to work your way around it, how to identify where the metals are, the non-metals, and so on. So if we look to the left-hand side of the table, all the way up to this blue line, okay, that's going diagonally down from boron, okay, all the way across here is the metals, and then to the right hand side of that blue line we have the non-metals. Okay, that's really important in bonding because in order to determine what kind of bond is needed, you need to identify whether something is a metal or a non-metal. If we look at diagram B, there we have an atom, okay, in very basic form. The center of the atom is a nucleus, and that contains protons and neutrons. So the protons here in this diagram are represented by those orange particles, okay, with the positive charge. The green particles just behind are the neutrons, and then those purple particles that are orbiting those the nucleus are the negatively charged electrons, okay. If we move on to C, we've just taken any of the elements from the periodic table and I've just chosen sodium. Now you'll notice the symbol is Na. Symbols always start with a capital letter and then end with a lower case letter. If there's only one letter, then it will always be a capital. Then it says sodium underneath to tell you the name of the element. And then you'll notice two numbers. The bigger of the two numbers, okay, which on this one is 22.9, so on, that is the mass number, okay. That is the number of protons and neutrons in the atom, okay. And then the smaller number is the number of protons, that's the atomic number. Okay, now you'll notice the periodic table of elements in section A there, the numbers are the other way around. The big number on the top of the symbol and the small on the bottom. Doesn't matter which way around, as long as you identify the biggest number as being the mass number, then that's great. You're not going to make any mistakes with that, okay? Then we move on to D, and here we have what is really important in bonding, in fact, is electrons and the electronic configuration of electrons around the nucleus of different atoms. Now we've got sodium here, okay, and sodium has 11 electrons, and we know that from the atomic number. So if we look back at C, you'll see that 11 is here, okay, that is the number of protons present in an atom of sodium. Now if there are 11 positive protons, there must be the equivalent number of negative electrons because all atoms are neutral. Okay, so we know there are now 11 electrons also in sodium. We can pop them around these orbitals, like in diagram D. Now, only 2 electrons can go into the first orbital, and in every orbital after that, we can have up to a maximum of 8. Now, as sodium has 11 electrons, that means 2 in the first orbital, 8 in the second, and that leaves 1 behind in the third. Now, that 1 outer electron is very important in bonding, and we're going to be looking at lots of examples using those outer electrons throughout the course of today's lesson. So to begin with, I would like you to try this little task of putting these into 3 categories, okay? So on the white side of the slide, we have various different metals, elements, and so on. And I would like you to tell me if they are metallic, ionic, or covalent, okay? So you might want to do a quick little list, 3 columns. Where do these fall? So, for example, water, is that metallic, ionic, or covalent? What kind of bonding do we see in water? Okay, so I'll just give you a quick minute to do that. Okay, so just a little more time. Have we put them into 3 categories, metallic, ionic, or covalent? What do you think? Where do you think they belong? Okay, I think then we'll have a look at the answers to see how you did. So metallic, okay, so here we have potassium, zinc, and mercury falling under metallic. And let's have a look at the other side of the table at covalent. So we've got water, HCl, which is hydrochloric acid, and carbon dioxide. So they are the covalent substances. And then in the middle, we've got ionic. Now, the reason why I've put some in bold and some not is I wanted to show you that ionic substances are made up of metals and non-metals. So if we look at sodium chloride, when sodium bonds or reacts with chlorine, it forms sodium chloride, okay? Sodium is the metal and chlorine, which forms the chloride, is the non-metal. And that's an ionic substance for you. Then if you move down, we've got copper and sulfate, we've got copper and oxide, okay? So there are your 3 different types of bonding. So here we go, just to give you more clarity on the types of bonding. We have metallic, which is the bonding present in metals only. Ionic, which, as I just said on the previous slide, is the bonding between a metal and a non-metal. Simple covalent, okay, which is between non-metals only. And then giant covalent, which is also non-metals, but on a bigger scale, okay? So we'll have a look at all 4 of those as we move on in today's lesson. Let's begin then looking at a metallic bond. So if you're asked to draw a diagram of the bonding present in metal, for example, sodium, okay, it could be any metal at all, but I've just chosen a metal from group 1. You'll see here what we have is a lattice of positive ions, okay? These are the sodium ions. And in order to form an ion, that sodium atom must have lost that 1 electron that it has in its outer shell, okay? Where have those electrons gone? Well, you can see they're represented here by these yellow circles. All these electrons are free. They're free to move between this structure, between this lattice of positive ions, okay? And as you can imagine, positive and negative, they are opposite charges and they attract. There's a strong attraction, which means that the bonding in a metal is very, very strong. And that results in high melting points, boiling points, and so on. Okay, so here we have a typical bonding diagram for sodium. If you were asked in an exam to produce a diagram showing the bonding in a metal such as sodium, you would draw something like this, okay? Maybe not with so many ions and electrons, otherwise it might take you the whole of the paper to do. So we would also say that it's got a sea of delocalized electrons. Okay, that's the way we would describe that in chemistry. Okay, a sea of delocalized electrons. Delocalized just means free. So let's have a look at a typical exam question where you have to compare between sodium metal and magnesium metal. So what's the difference here in terms of their bonding? Now, as we've already seen, sodium, okay, sodium ions are +1, so they're represented here with the plus the plus shapes on this diagram, okay, the circles. And then the red circles represent the free electrons surrounding those positive charges. Now, the difference for magnesium, well, hopefully you can see we've got double the positive charge for each of these ions, and that means you've got double the number of electrons surrounding those ions, because each one of those atoms has lost 2 electrons for magnesium rather than 1 in sodium. Now, if there are more charges, how do you think that will affect the metal? Let's have a look. Magnesium has more positive and negative charges in the lattice structure. So as we said, there are more positive charges. Each ion is 2 plus now rather than 1 plus. And also there are more electrons because of this. That means the electrostatic forces between opposite charges are greater. There are more positives, more negatives, and therefore the attraction is greater. And that means that the melting and boiling points of magnesium also greater than that of sodium. Okay. So that same trend will move across as you go into group 3 as well, where you've got 3 plus ions forming and therefore 3 electrons surrounding each of those positive ions. So that's it on metallic bonding. So we're going to move now onto ionic bonding, okay, which is different. The bonding diagram requirements are different. And the first example we've got here is sodium chloride. Okay, now you might notice you've got the sodium ion here represented in square brackets, and the charge of the ion is placed outside the brackets. For chlorine, okay, chlorine in fact gains an electron, so the charge outside the brackets this time is negative because it's gained something negative. It's gained an extra negative electron. So what is an ionic bond? Well, when a metal and a non-metal react together, the metal will donate 1 or more electrons to the non-metal in order to gain a full outer shell or orbital. In the same way, that chlorine in this example wants to gain that 1 electron in order to have a full outer shell of electrons. Okay, full shells means they are stable and happy, okay, and a strong ionic bond will form as a consequence or as a result of that. So the result of those electrons getting lost and gained means you form ions, and these ions have opposite charges. Strong electrostatic forces of attraction form between those ions, so positive and negative attract, and that is what an ionic bond is. Okay, it's the electrostatic force of attraction between ions with opposite charges. Now, with a question, an exam type question, you're often asked to draw the bonding present in something such as sodium chloride. And I would always go about it in this way, okay? First of all, identify what elements you have in sodium chloride. So we've got sodium and we've got chlorine. Okay, and I would also suggest or recommend that you write down the information you know about sodium and chlorine, which of course you just take from the periodic table, which is in your exam paper. Once you have that information, you can see how many electrons sodium and chlorine have. And then it's important that you write out the electronic configuration for those 2 elements. So for sodium, it has 11 electrons, and therefore the electronic configuration is 281. That's important because it tells us there's 1 electron in the outer shell. Chlorine has 17 electrons, and therefore the electronic configuration is 287. It has 7 electrons in its outer shell. Now we know that that atoms need 8 electrons in their outer shell if we're talking about every shell that isn't the first. Okay, the first needs 2, and after that 8 in each one. So that means sodium must lose that 1 electron and chlorine must gain 1 electron, and in doing so they will then be happy, stable, and form those ions. So to draw the diagram before bonding, then we show the 1 electron present in sodium as a cross, and you can see that being transferred by this arrow, okay, which is drawn here, showing the electron transferred over to chlorine into this space present here. Can you see also that when you draw electrons, that we put them in pairs, we've done them 2, 2, 2 together. That just makes it much easier for you when you're counting, and also less likely to make mistakes, okay? If you've just drawn the electrons all over the place, it might be hard to keep track of how many you've got. So I'd recommend you put them into pairs to make it clearer for you. So once that electron transfer has occurred, we'll then move over to after bonding, and this is the formation of the ions. So sodium this time has lost that 1 outer electron, and that means we move down now to the next shell in, which has got 8 electrons. Okay, and that is shown in this diagram, but we mustn't forget about that 1 outer electron that was lost. So that is shown by the positive sign outside of the square brackets. That's to show that sodium has lost something negative, so has become 1 positive. Okay, chlorine, on the other hand, has gained that 1 electron. We show that with a cross on that diagram. Okay, the rest of the chlorine electrons are circles, just to show the difference. And there's a negative charge outside the square brackets to show that it is an ion as well. Notice on the bottom we have the new electronic configuration for both sodium and chlorine. And the formula, as these two are now attracted and forms an ionic bond, is NaCl. Okay, notice here as well, I've got the capital N, small, so lowercase a, capital C, lowercase l. Now that shows me that there are 2 elements in this bond here, in this ionic bond, sodium and chlorine, and you've formed sodium chloride. So it's time now for you to have a go at this, okay? I would like you to draw a bonding diagram for magnesium chloride. I've popped magnesium and chlorine down there on the screen for you already, just to have a look at to help. Okay, but again, in your exam, you would be looking back and forth to your periodic table. So have a go and see if you can show me the ionic bond in magnesium chloride. Okay, so if you need more time, remember you can just stop this at any time and work through this question. But I'm going to show you the answer now. So here we go, we've got magnesium electronic configuration, which is 282. Okay, that means there are 2 outer electrons. And then chlorine, the electronic configuration, which is 287, meaning that there are 7 outer electrons. Okay, now slightly different, slightly more complicated than the previous example, in that this time magnesium has to get rid of 2 electrons. So all we need to do is have 2 chlorine atoms in order to accept those electrons. So 1 electron will go to 1 chlorine, 1 will go to another, and therefore this will be shown in the after bonding by this 2, which is put just before the square brackets for your chlorine ion. Okay, that shows that 2 chlorine atoms were needed in order for this ionic bond to form. Magnesium, you can see this time we've got 2 plus as the charge because it's lost 2 negative electrons. And chlorine has 1 minus, okay, because each chlorine has only gained 1 electron, but there were 2 of them, so we show that with 2 before the square brackets. Lots of mistakes usually made here where students will put 2 minus as the charge, okay, which is incorrect because only 1 electron was gained by each chlorine, so it's still -1. The formula then is MgCl2. Remember the 2 being subscript, okay, to show that there were 2 chlorine atoms involved in this bond. Well done. Now here's another exam question. Now this is a 6-mark question, okay, the one that I came across. So lithium chloride is a solid with a high melting point. It conducts electricity only when molten or in solution. Describe the bonding present in lithium chloride and explain the properties given above. So they've kindly given you the electronic configuration for lithium and chlorine. Okay, The first thing here, and where lots of mistakes are made, is identifying what type of bond is needed, what type of diagram, bonding diagram is needed here. So if you're not sure, have a look at the periodic table. What is lithium? Lithium is a metal, it's in group 1. What is chlorine? It's a non-metal, it's in group 7. Once you know you've got a metal and a non-metal, then you should know you have to make an ionic bond. Okay, so have a go at that. I will come back in a minute and go through the mark scheme with you. Okay, so if you need more time, remember, just pause this and restart it when you're finished. Okay, so here we've got quite a lot of information here, in fact, okay, but this is the mark scheme for this particular question. So first of all, there's a diagram there showing the bonding in lithium chloride, okay? So I know it's not very clear on here, but you can see there's a transfer of an electron from lithium to chlorine, okay? And that forms your lithium plus and chlorine, chloride minus, sorry, ions, okay? Now, what they're looking for here is a description of the bonding in words, so such as lithium atom loses an electron to become a positive ion, chlorine atom gains an electron to become a negative chloride ion, and that those opposite charges then attract, okay? In terms of properties, well, it has a high melting point because of the strong bonds between those oppositely charged ions. It conducts electricity when molten or in solution, because when it's molten or in solution, those charged ions, the Li plus and Cl minus, are free to move. And the movement of charge is current. So that's, you know, the ability to conduct electricity then, okay? It does not conduct when it's a solid, as obviously those ions are not able to move. So in order to get the maximum marks, a lot of that information there will be in your answer. Also, think about, you know, don't make mistakes between atom and ion. Lots of mistakes are lost there. Make sure you've got the right charges and so on. So have a look at that mark scheme. That's a really good question there. A really good example of a question that you might have. Next, we move on to my favourite bond. This is the covalent bond, which is all about sharing, which is nice, sharing of electrons. Covalent bond is a bond that forms between one non-metal and another non-metal. Okay, the atoms in a covalent bond share electrons in order to achieve a full outer shell. So this time there's no transfer of electrons. One is getting rid of, one is gaining. This is all about sharing electrons. When a pair of electrons are shared between two atoms, this is called a single covalent bond. Okay, now when we talk about covalent bonds forming between non-metals, they can be the same non-metal, such as in this diagram here with the two chlorine atoms, or it could be with different ones, such as an H and a Cl, or various other examples of that. Okay, so once again, if you're not sure what type of bond is needed, have a look at your periodic table and find out if your element is in fact a metal or a non-metal. So let's have a look at how we would go about doing the bonding diagram for something such as methane. Okay, now methane, CH4, consists of carbon and hydrogen. So the first thing, just as in the ionic bonding diagram, you need to identify the number of electrons and put those down within an electronic configuration. So for carbon, we've got 2 and 4. That means there are 4 outer electrons. And with hydrogen, there's only the 1. So the number of outer electrons is also 1. Okay. Right, so what do we need? Well, we need carbon to have a full outer shell of electrons, and we need the same for hydrogen. Please note, hydrogen is only in its first shell. So hydrogen, in fact, only needs one more electron to gain a full outer shell of electrons, because remember that first shell only requires 2 to be full. Carbon has 4 electrons but needs an additional 4 in order to have a full outer shell of electrons. So how does it go about doing that? Well, if the carbon forms a covalent bond with 4 hydrogen atoms, then it will share 1 electron from each of those hydrogen atoms. And then if we have a look around that central circle, the central carbon there, if we count up those electrons, we now have 8 electrons, okay, 4 crosses and 4 red circles. That gives carbon 8 electrons. But also, because of the sharing, each hydrogen is gaining 1 electron from the carbon. Okay, so the hydrogen atoms also now have 2 electrons, which means they have a full outer shell of electrons as well. Hopefully that wasn't too confusing for you. Okay, the best thing to do with covalent bonding is to practice them. Okay, because once you have done so many, there won't be that many more examples that they could ask. So practice as many examples as you possibly can. The formula then is CH4. And remember the 4 showing the 4 hydrogen atoms as subscript. So let's have a go with another example then. Okay, this is ammonia, and ammonia contains nitrogen and hydrogen. So I'll give you just under a minute just to have a look, pull the information out, the electronic configuration, number of outer electrons and so on, and let's see if you can show me the bonding diagram for ammonia. Okay, so I'm going to show you the answers. Stop if you need more time. So here we've got the electronic configuration for nitrogen is 2.5 because there are 7 electrons. That means there are 5 outer electrons, and then hydrogen, obviously we've just had a look at that one. It's got 1 outer electron. If nitrogen has 5, it needs an additional 3 electrons in order to have a full outer shell of electrons, and therefore needs to form 3 covalent bonds with 3 hydrogen atoms. And that's shown by the diagram here. So you can see that we've got 3 shared pairs of electrons, and nitrogen also has this pair of electrons which are not being shared. Okay, this is called a lone pair of electrons. They're not involved in bonding in the covalent bond, okay, but are involved in bonding in a different way, which you will find out if you move to do AS chemistry. Okay, the formula for ammonia is NH3. Well done if you got that right. So there's another question here for you to have a look at. The bonding in oxygen O2 is also covalent, so it's given you that bonding at least. Draw a dot and cross diagram to show the bonding present in a molecule of oxygen. So it's given you the electronic configuration. You can see there are 6 outer electrons, and so oxygen needs an additional 2. We know that oxygen exists as O2, so there's a clue that there needs to be another oxygen there. So if you want to have a go at this, stop this now. Otherwise, I'm going to move on to the mark scheme. All right, so here we go. Slightly more difficult, more complicated one, this one, okay, because this time we've got 2 pairs of electrons being shared, okay, because each oxygen needed an additional 2 electrons. Now, before we've seen just 1 pair sharing, and that is a single covalent bond. But when you get an example such as this one, where you've got 2 pairs of electrons sharing, okay, that is called a double bond. So each pair is the equivalent of 1 bond. So if you've got 2 pairs, it's a double bond. We're going to move on now to giant covalent structures. And these are solid substances with very high melting and boiling points. And the majority that you will study at GCSE Chemistry level are different physical forms of carbon. Now, we call these different forms of carbon allotropes. Okay, so that might be a word that you've come across before. The most common is probably diamond and graphite. Okay, these are both allotropes of carbon because they are made of carbon only. So what's the difference between diamond and graphite? Well, before we go through that, I just want to bring you to have a look at carbon from the periodic table. You can see here that we've got 6, okay, electrons present in carbon. Remember, if the number of protons is 6, the number of electrons is also 6. That gives you an electronic structure of 2.4, okay, which means that each carbon can form 4 bonds, okay, because it has 4 outer electrons. Keep that in mind. Let's have a look at diamond to begin with. And I'm sure you all know what diamond looks like, okay. Nice and shiny, very pretty, used for making various jewelry and so on, okay, or drill bits because it's very, very hard. But the structure itself looks like this here, okay. Can you see? If we focus on one of these circles, okay, this is one carbon atom. So each of these circles, each of these spheres you can see here are representing one carbon. If we look at one of them and count how many carbons are bonded to that central carbon, you'll notice there are 4. So in diamond, every single carbon atom forms 4 bonds. Now, remembering back to what we just said, carbon can form 4 bonds because it has 4 outer electrons. That means if every carbon that's present in diamond is involved in forming a bond, there are no free electrons anywhere. There's no sea of delocalized electrons. They are all involved in bonding. So if there are no free electrons, that means diamond does not conduct electricity because charge cannot flow. And as I've already said, diamond is a very hard substance. That's due to the structure of diamond. This lattice of carbon atoms bonded in this way means it is very hard. Now, graphite, which is found in pencils, okay, is what you write with, is very different. It looks different. You can see you've got these layers and you've got this gap between the layers. Now, let's have a look at one carbon atom here. So remember, this is all carbon as well. So choose one of these circles and count how many carbon atoms are bonded to it. You'll notice there are 3. So this time, rather than each carbon atom forming 4 bonds, there are in fact 3 bonds. So what that means is 1 electron for each carbon atom is not involved in bonding and therefore is free and moving around, okay? And those electrons, they tend to move around between these layers, okay? If we've got a movement of electrons, then obviously it will conduct electricity. So graphite conducts electricity. That what's present in your pencil. I don't know if you've ever tried making circuits using a pencil, but that will actually work. You can use the graphite in a pencil, connect it up to a battery, an LED, for example, and it will make that LED light up. One other thing we know is that it's soft. So when you're writing, the reason why you leave a line on your paper is because those layers are breaking off because graphite is in fact very soft. Okay, more giant covalent structures. Well, here we've got graphene, we've got nanotubes, and we've got Buckminster fullerene. Okay, also made up of only carbon atoms. Okay, the 3 of these, in fact, to make it easier, each carbon forms only 3 bonds, just like in graphite. So you've probably guessed it already. That means there's 1 free electron to move for each carbon atom present, and all 3 of these will conduct electricity, therefore. They all have different properties, special properties, okay? This kind of technology is really growing. It's a very exciting industry and something that maybe some of you might consider going into when you leave school. So here's some questions for you, some giant covalent bonding questions. So you've got diamond, graphite, and a carbon nanotube here. And the question is, two of the structures shown above conduct electricity. Name both and give the reason why they're able to conduct electricity. So I'm going to move on to the mark scheme because we have already discussed that answer. The two that conduct electricity are graphite and the nanotube, and that's because they have free moving or delocalized electrons. Diamond, of course, does not, because each electron is used in bonding. Another question for you. So you've got 4 diagrams there. When you see something like this, hopefully your brain is ticking over as to, trying to identify what A, B, C, and D are. Give the letter of the structure which represents diamond. Name an element that has structure D. Give the letter of a structure which is able to conduct electricity. And give the letter of the structure that represents sodium chloride. So let's have a look at the mark scheme. So C is in fact diamond. I'm sure you've got that. Name an element that has structure D. So you can see D here is showing the bonding diagram of a metal. And because each one of these spheres, these circles, have got 1+ charge, that means you can choose any metal from group 1. We're accepting sodium, lithium, potassium. In fact, in this mark scheme, they're also accepting any other metal. Okay, so you could even go with magnesium, even though it should really be 2+ in each one of these positive ions. Give the letter of a structure which is able to conduct electricity. So we've got A and D. So A is the graphite, where you've got the free electrons between layers, and D, obviously, those electrons, the sea of delocalized electrons around those positive charges can move. Okay, and finally, maybe one that you wouldn't be so sure of or wouldn't be so familiar with is the structure that represents sodium chloride. So sodium chloride is a lattice structure where you've got alternating sodium and chlorine. Okay, and it's shown here with the different circles. Okay, so you've got the larger one, which is the chloride, and you've got the smaller, which is the sodium. Okay, moving on, we've got some additional questions to finish. So these, again, taken from previous exam papers. Draw a line to link each substance with this structure, and you can see one's been done for you. So we've got matching those up, and then question 2, give the electronic structure of sodium, and then draw a diagram to show the metallic bonding in sodium. So let's have a look at the mark scheme. So graphite is in fact giant covalent, potassium is a metal, so the bonding would be metallic, and sodium chloride is ionic, sometimes seen as giant ionic. So if you see giant ionic, don't confuse that with giant covalent. Okay, and then we're looking at sodium, has an electronic configuration of 281. And here is a typical diagram for sodium. Again, you can see it's got +1 ions to represent the Na+ ions, and then we've got this sea of delocalized electrons then around that. So what they're looking for here is positive ions in fixed position. So we want them, in these nice rows, and then we want these electrons all around these positive ions to represent the sea. And then finally, we finish with these 2 questions. Give the electronic structure of sodium and oxide ions. Now, this is a really important question to point out to you, because it does often catch students out. It's not asking for the sodium metal, okay? It's asking for the ion. So in order for sodium to become an ion, it will have lost that one outer electron. So think about that, okay, with your electrons. And then the oxide ion, in order to become an oxide ion, it must have gained 2 electrons. Okay, so all you would do was put the original electronic structure down for these atoms, but then add or take away electrons depending on whether it's a metal or a non-metal. Name the type of structure present in ammonia and explain why ammonia has a low melting point. Let's have a look at these mark schemes to finish off. So we've got sodium ion, which is 2,8. It would have been 281, as an atom, but remember he loses 1 electron to become 2,8. And then the oxide ion being 2, so oxygen being 2,6, but when it becomes the oxide ion, it gains 2 electrons to become 2,8. Really important that you have a look at that. And then the type of structure present in ammonia, it's basically asking for the bonding, okay, and that is simple molecular, okay, or if you put down covalent, that's exactly the same. Why ammonia has a low melting point? Because even though covalent bonds are strong, the attraction between molecules, so one ammonia molecule and another ammonia molecule, is actually very weak. So these can break apart really easily with a little bit of energy. Only a small amount of energy is needed to break them. So there we go. Lots of things for you to think about, lots of questions. Please, please, please make sure you have a good look at the periodic table, that you know your metals, your non-metals, and therefore you can identify the correct type of bonding diagram in order to get those marks that you need. Okay, thank you very much. Diolch yn fawr, and I'll see you at a different session.